Thank you for your interest in this talk. Today I'm going to talk about state-feedback abstractions for piecewise-affine systems. My name is Lucas, and this is a work that was carried out with Thiago Alves Lima and also Rafael Jungers at UC Leuven in Belgium. So my presentation today is organized in this way. First, I will introduce what's abstraction-based control and give some motivations for this current work. Then I will formulate the problem we're going to study. I will introduce state-feedback abstractions, which is a concept we developed in this paper. And finally, I will show in examples how it can be applied to optimal control. So traditionally, in abstraction-based control, we discretize our state space, and here it's being represented by these squares. I'm going to call each square a cell. It's going to be a set of states in my state space. And for each one of these states, for each possible input that I have in my system, maybe I have a finite number of inputs. Here I will have U0 and U0 prime, but maybe I have a continuum of inputs, and then I can discretize this continuum set and obtain a discretized set. So for each one of these inputs and for each one of these cells, I'm going to calculate the image of the cells over time. So if I do this for this cell here, for instance, I'm going to end up with these two images. Once I have these images, now I have to reason on which cells in my state space these images intersect. So associated to each one of these cells, I will create a node in a graph. So here I'm denoting this by these balls. And then I can see that the green image associated to U0 intersect these four cells over here. So in my graph, I will add transitions from my initial cell to these other cells corresponding to the U0 entry. I will do the same for the U0 prime. So I see that the orange one intersects these four cells over here, and that's why I added these transitions towards these nodes. Then my graph is going to be what I call an abstraction. And looking at this abstraction and reasoning upon it, I can take some decisions that I can apply to my real system. So for instance, imagine that here I have an obstacle. So whenever I'm here, I know that I should not apply U0 prime because there's a probability that I will end up in this state. In the same way, imagine that one of these four cells is my goal state, my target. So there's a high probability that I want to apply U0 while I'm here because there's a chance that I will end up with one of these. So one thing that we notice is that whenever I have an unstable system and apply a constant input, I see the image or some over-approximation of my image growing over time in terms of size or in terms of volume. And that's something that will add non-determinism to my system. I will be less and less certain about where I am over time if I only look at the image of the cell. But if I apply this other input of this form here, which is also constant, but is not applied uniformly over all the cell. It's applied, we have different values from depending where I am in the cell with respect to its center. So if I apply this other constant input U, then I will see that the shape of my image will change, and it may even shrink if this K was chosen appropriately. And if I do exactly the same thing as I did in the previous slide, I build the abstraction based on the images and which cells they intersect, I will see that for the constant red input in uniform, I will have way more transitions than for my blue one. Which is also constant, as I said, but is not uniformly applied over the cell. This allows us to reduce the non-determinism of the system, and this is the idea that we're going to explore in this work. So we're going to study an optimal control problem, and we're going to focus on non-deterministic piecewise-affine systems in this work. These systems are given by this difference inclusion over here, where F is a set-valued map, which is composed by an affine dynamics plus some uncertainties. So first, psi is going to be an index function which will associate to each state one of the parts in my piecewise-affine partition. So this can be seen as a state-dependent switching system. The matrices AI, BI, and GI, we're going to define a nominal system, the ith nominal system, and I'm calling it nominal because it's excluding any noise, any possible non-determinism. And the non-determinism is actually captured by the set omega, which can characterize, for instance, an exogenous input, some uncertainties, or maybe this is a nonlinear system that was approximated by a piecewise-affine one, and then every error on this approximation is captured by this omega set. Therefore, having this setup, I can state my optimal control problem as being take every possible state x from the initial set x naught towards the goal set x star while avoiding some obstacles and minimizing a cost function c that I will define shortly. To tackle this problem, I'm going to present state feedback abstractions. And to define state feedback abstractions, first I will define a transition system for my piecewise-affine system that I presented in the previous slide. So I will call this system S. This is going to be my concrete system, and it will be defined by this tuple. So X is going to be its state space. It can be a bounded state space. U is going to be the input space. It can also be a bounded one. And this set over here is going to be the set of transitions. And it's built in a way that I will be sure that if there is a transition in this system, it's because a transition from X to another state X prime under input U will satisfy the difference inclusion that defines the system. Then I can define another transition system, which is this one. This is going to be my abstraction, S tilde. And its state space is going to be XD. It's a set of cells in my state space. So cells are subset of states in my state space. K is the set of inputs for my abstraction. In this case, these are going to be functions. These are going to be controllers mapping X to U's. This can be continuous functions over X, and I'm going to define them appropriately later. So finally, you have the set of transitions, and this transition is going to be built in a particular way. So I'm going to have a transition in my abstraction from one cell psi to another cell psi prime over a controller K, if and only if I'm sure that this controller K maps every X inside my initial cell psi into another into this other cell psi prime. And this is actually what will characterize a state feedback abstraction. If this is true, then S tilde is a state feedback abstraction of S. And it's very interesting because this is a deterministic system. And to illustrate that, here I have two cells, psi and psi prime of my abstraction. Then I will have some controller K that maps everyone in the first cell into the other cell. And this will ensure me that whenever I am anywhere inside this first cell psi, there will exist some input U that will bring me into the other cell psi prime. This is very interesting because this characterizes the existence of an alternating simulation relation between my abstraction and my original system. And this is a very powerful relation that will allow us to do optimal control in this case. So having an alternating simulation relation between my abstraction and my original system will first allow me to use theorem 2, which is generalized from this other reference over here. And it says that if there exists a Lyapunov-like function for my abstraction, then there exists also another Lyapunov-like function for my concrete system. And the nice thing about this theorem is that the proof is constructive, so I can always construct a Lyapunov-like function for my concrete system out of a Lyapunov-like function for the abstraction if some conditions are met. And I'm not going to go into the details of these conditions, but I will recall that later in the presentation. So Lyapunov-like functions are important because first they ensure an upper bound on the cost to go function, and that will help me to solve an optimal control problem. It also ensures safety. We know that level sets of Lyapunov functions can be used as barrier functions. And finally, it also ensures reachability of sets for deterministic systems, and we have a deterministic abstraction over here. So the question now is how to build a state feedback abstraction. Well, to do that, we're going to look at a single mode of our piecewise-affine system now. It's going to be equivalent written in this way, where omega is a disturbance that takes value into a set omega that is supposed to be polytopic here. Then we want to verify the existence of a controller, which is a function kappa of the state x, that will ensure a transition from initial set, starting ball S, defined as an ellipsoid like this towards a final ball BF, also defined as an ellipsoid like this. I want this controller to respect input constraints that are given in this shape over here. And the fact that I'm searching for functions or controllers of this form will help me avoid discretizing the input space, which is particularly interesting when this input set is unbounded. So actually when this input set is unbounded, it even helps us because we have less constraints on our controller. To verify the existence of a transition respecting all these, we have theorem 2, which presents a necessary and sufficient condition for the existence of a controller of this form, respecting the input set and also ensuring the transition from BS to BF for any possible disturbance omega in the disturbance set. This is true if and only if there exists scalars like this and this matrix and this vector satisfying this set of LMIs over here. This is very interesting because verifying the existence of a controller or deciding if a controller exists can be efficiently done by SDP programming by solving a feasibility problem over these LMIs. But unfortunately, this is not enough for doing optimal control. We also have to somehow bound the stage cost, the cost of transitioning from one stage to another. And to do that, we're going to consider a cost function like this. Is the accumulated sum of this function j, and j is going to be what we call the stage cost. It's a quadratic function on x and u, is a general quadratic, and it's general enough to represent the quadratic costs like these that we have in LQR controllers, or time costs, or composition of boths, and we even can generalize that to cope with 1 and infinite norms. And then we can, in this context, bound the transition cost for each transition by the results of corollary 1. And actually it says that the optimal solution of this convex optimization problem that I have over here will ensure the controller providing a transition from BS to BF, and also that J tilde, the optimal value of the optimization problem, is exactly the worst case transition cost when I'm in cell BS and apply the controller kappa of X. This, very fortunately, is exactly the condition that we needed for theorem 2 to construct Lyapunov-like functions from our concrete system. And it's very important to highlight that this is just not an upper bound. This is exactly the worst case transition cost that we have in this setup. Then designing a transition can be done efficiently by convex optimization, and we don't have to discretize input space to build our abstraction. We also have tight upper bounds on the stage cost, and that's because we didn't introduce any conservatism in developing these conditions. To assess some underlying necessary conditions associated to our method, we're going to focus now on a very special case. We're going to consider that there exists an exact map between two balls, and by that I mean that the center of the starting ball can be mapped exactly at the center of the final ball by some input u, and there are going to be no noise, and both sets are of the same shape. They're just translated versions from one another. And in this case, one underlying necessary condition of our method is the stabilizability of the pair AB. And it actually gives us a good hint on how to choose the shape of the ellipsoids. I can find a stabilizing controller for the system and solve the Lyapunov equation, get the matrix P that solves it, and call P and P plus this solution. If I didn't have a linear gain K in my controller, if this controller was constant and uniform all over the cells, then a necessary condition for a transition to exist in this case we're going to be the stability of matrix A. And this is known to be a way harsher condition in control theory. So out of this, we conclude that having this K will help us reduce the non-determinism of my system and also allow me to build a deterministic abstraction even when I don't have incremental stability of the system. To illustrate that in an example on optimal control, I will consider this piecewise-affine system over here. I will have a partition with 3 parts of my state space defining by these matrices over here and these sets in the first line. I will also have additive noise defined by these boxes, constraints on my input set, constraints on my state space. I will consider some obstacles as well, and my stage cost is going to be defined like this. Now my goal is going to be to get any possible initial condition out of a set x naught towards the set x star, while minimizing some cost function given like this. To build this abstraction, I will first define a set of cells, which is going to be a lattice of balls of radius 0.2. To design the set of controllers in the transitions, I'm going to run the convex optimization problem that I showed in the previous slide. And this is going to be done pairwise to cells, but I'm not going to test all pairs of cells. So I have an efficient way to rule out cells that they're not promising to have transition towards them. So I do that for a subset of all the pairs of cells. And doing that, after about 200 seconds, I found the 7,000 transitions in my abstraction, and could build this graph, which is my abstraction. It's a deterministic graph. So I can use Dijkstra's algorithm on this resulting graph to find first the minimum cost path from my initial set x naught to x star, and also a Lyapunov-like function on a part of my state space. This Lyapunov-like function is depicted here. So the color map defines the value of the Lyapunov-like function. This is my initial set, this is my final set, this is some obstacle, and these balls in white are cells for which no Lyapunov-like function could be defined. So we can see that here in blue we have one trajectory starting from x naught and attaining x star under the controller that was designed by Dijkstra's algorithm. And this shows how this method can be applied in optimal control under complex specifications. So in this work, we formalize the state feedback abstractions. We provide the efficient way to build them for piecewise-affine systems, and also showed how this can be applied in optimal control problems, also for piecewise-affine systems. And in the future, we plan to come up with an iterative way to update centers and shapes, and also explore the idea that sometimes I want cells to contract, and sometimes I can allow them to expand and pay fewer control effort to do that in that step. And finally, we would like to explore random tree-based methods and also data-driven approaches to avoid discretizing the state space as well. So thank you very much for your attention, and also thanks ERC for sponsoring this work.